In this video, we will introduce concurrency fundamentals within the Java programming language using threads. When you work with a computer, you can do several things at once. You can hear music while you edit a document in a word processor and read your email at the same time. This can be done because your operating system allows the concurrency of tasks. Concurrent programming is about the elements and mechanisms a platform offers to have multiple tasks or programs running at once and communicate with each other to exchange data or to synchronize with each other. Java is a concurrent platform and offers a lot of classes to execute concurrent tasks inside a Java program. We're going to be looking at creating threads by extending thread, creating threads by implementing runnable, the advantages of using threads. We will look at different thread advantages, like the fact that threads are lightweight compared to processes, the fact that threads share the same address space and therefore can share both data and code. We're also going to be looking at daemon threads. A daemon thread is a thread that does not prevent the JVM from exiting when the program finishes, but the thread is still running. We're also going to be looking at thread states, thread problems, synchronization. Now let's begin. In this video, we will introduce creating threads by extending thread within the Java programming language. What is a thread? When a modern operating system wants to start running a program, it creates a new process. A process is a program that is currently executing. Every process has at least one thread running within it. Sometimes threads are referred to as lightweight processes. A thread is a path of code execution through a program, and each thread has its own local variables, program counter, and lifetime. Most modern operating systems allow more than one thread to be running concurrently within a process. When the Java Virtual Machine, or JVM, is started by the operating system, a new process is created. Within that process, many threads can be spawned or created. In this lesson, I'm going to show you just how simple it is to get a new thread up and running in a tiny Java application. The first thread is the main thread that is always spawned by the Java Virtual Machine and starts an application. This main thread then spawns the second thread. Each of these threads will print its messages to the console to demonstrate that they both appear to be running simultaneously. Let's take a look at our code. In this method, one normal class extends the inbuilt class thread and override its run method with the code required by that particular thread. So here we extend the thread and we override the run method. Here we are going to extend the class so we can access all the methods of thread class. Create one class which extends the thread class. Application execution begins with the main thread, which is spawned by the JVM for all applications at startup, entering the main method. It proceeds to create an instance of the demo class, which we saw above, which extends thread. Next, it spawns a new thread of execution by invoking the start method. This new thread will begin its execution by invoking the run method of the demo class. After the main thread spawns the new thread, the main thread proceeds into its loop and prints demo thread to the console 10 times, or 5 times. When it is done with the loop, it falls through and returns from main. The main thread dies when it returns from the main method. At approximately the same time, the new thread enters the run method, proceeds into its loop, and prints another thread to the console 5 times. When it is done with the loop, it falls through and returns from run. The new thread dies when it returns from run. Let's run our program and see this behavior. Right-click on Source, Run as Java Application. Thread scheduling is non-deterministic and depends on many factors, including what else is currently running in the operating system. The thread scheduler makes what seems to be random decisions about how long each thread should be allowed to run between context switches. The only thing that can be counted on from running this application is that each message will print exactly 5 times, regardless of the order of the messages. And we can see that in our output. This concludes our discussion of creating threads by extending thread in Java. In this video, we will introduce creating threads by implementing runnable within the Java programming language. The runnable interface should be implemented by any class whose instances are intended to be executed by a thread. The class must define a method of no arguments called run. This interface is designed to provide a common protocol for objects that wish to execute code while they're active. For example, runnable is implemented by class thread. Being active simply means that a thread has been started and has not yet been stopped. What is the difference between implementing runnable and extending thread? By providing a runnable object, the runnable interface defines a single method run meant to contain the code executed in the thread. The runnable object is passed to the thread constructor. The runnable interface represents a task which can be executed by either plain thread or executors or any other means. So logical separation of task as runnable, then thread is good design decision. Separating task as runnable means we can reuse the task and also has the liberty to execute it from different means, since you can not restart a thread once it completes. Again, runnable versus thread for tasks, runnable is the winner. One difference between implementing runnable and extending thread is that by extending thread, each of your threads has a unique object associated with it, whereas implementing runnable, many threads can share the same object instance. A class that implements runnable is not a thread and just a class. For a runnable to become a thread, you need to create an instance of thread and passing itself in as the target. In most cases, the runnable interface should be used if you are only planning to override the run method and no other, and leaving all the other thread methods the way they are. This is important because classes should not be subclassed unless the programmer intends on modifying or enhancing the fundamental behavior of the class. Now let's implement the runnable interface. Here we can see in our main method that we have a runs class, which is an inner static class which implements runnable. Inside, we override the run method. We do is print out our location. We go through a for loop, printing 10 times that we're inside this run method, and then we exit, printing out again to the console. Here we create a thread. By creating this thread object and giving a reference of class object to thread object, basically starting and implementing our run method through our runs implementable runnable. To get it started, we have to call start on our thread, which target is our runs object. Here we will end our main thread, which starts here in our main method. Let's run our program and see the output. Right-click on the source, run as Java application. Here we can see our output. This concludes our discussion of creating threads by implementing runnable in Java. In this video, we will introduce the advantages of using threads within the Java programming language. When you work in a computer, you can do several things at once. You can hear music, watch a video, edit a document in a word processor, and read your email. This can be done because your operating system allows a concurrency of tasks. What are the advantages of using threads? Advantages of multithreading over multitasking. Multithreading reduces the computation time, improves performance of an application. Threads can share the same address space, so it saves memory. Context switching between threads is usually less expensive than between processes, such as in multitasking. The cost of communication between threads is relatively low. It also keeps a process responsive. Sometime back ago, to print a document in Microsoft Word, the application would freeze until the print job finished. You had one fleeting opportunity to cancel before you were firmly committed to waiting before your printer slowly printed up to the last page. Microsoft and other software companies fixed this behavior by running print jobs on a separate thread. Developers, when having to make a decision that a particular task could take a long time to complete, and that task should be run apart from the user interface thread, have had to implement multi-threaded applications. Not just as GUI apps or desktop applications, but network services have also needed to be multi-threaded to do heavy lifting on a secondary thread to keep the customer satisfied. Keeping a processor busy. No matter how fast your CPU is, if it is not actively processing, the CPU speed becomes irrelevant. Keeping a processor working can be a difficult task. You see, there are all kinds of things that could cause a processor to idle away time. The most prevalent and common is disk and network I/O. When a single-threaded application accesses a file, calls out to a web service, or streams from a USB webcam, your processor is just killing time. Occasionally, there isn't much you can do but wait for the I/O to complete. But there is something else you could do. You could spin up while you were waiting for the process to finish. If you're processing a series of files, you can process one file while reading the next. If you're calling multiple web services, call them in parallel. Maybe one will come back before the other. Try to think ahead. Keep multiple processors busy. If you run multiple processes, that is, multiple distinct applications or multiple instances of one application, the operating system will continue to rescue and goad those other processors into action. But if you want your specific application to wrestle maximum horsepower from the hardware it's on, you've got to give the OS scheduler multiple things to work on simultaneously. And the way you could do this is through multiple threads. Simplifying code of cooperating. If you think about it, most software bugs come from either doing sometimes something difficult or doing simple in a difficult way. Sometimes you end up writing code that trips over itself trying to advance multiple tasks at once. Just as many programming problems have both an iterative and recursive implementation, many programming problems also have both serial and concurrent variations. The version you choose depends on the nature of the specific problem. Try to write a multi-client network service with just one thread. Though possible, particularly if you're savvy with Sockets API, it isn't natural. When you refactor it into threads, the code becomes logically simpler. One thread per client, one thread to rule them all. The key in using threads to simplify your code is to try to keep your functions and methods on one train of thought. Rather than turn your code into an arithmetic problem, try to interleave multiple simple simultaneous tasks. Code each task separately. Code each line block with one in mind. Let the OS thread scheduler do the interleaving. This concludes our discussion of the advantages of using threads in Java. In this video, we will introduce daemon threads within the Java programming language. There are two types of threads in the Java system: daemon threads and user threads. The implication of these names is that daemon threads are those threads created internally by the Java API, and that user threads are those you create yourself, but this is not the case. Any thread can be a daemon thread or a user thread. All threads are created initially as user threads. Some threads that are created by the virtual machine on your behalf are daemon threads. A daemon thread is identical to a user thread in almost every way. It has a priority, has the same methods, and it goes through the same states. In the terms of scheduling, daemon threads are handled just like user threads. Neither type of thread is scheduled in favor of the other. During the execution of your program, a daemon thread behaves just like a user thread. The only time the Java Virtual Machine checks to see if particular threads are daemon threads is after a user thread has exited. When a user thread exits, the Java Virtual Machine checks to see if there are any remaining user threads left. Let's look at an example of this. Here we have a class, demo, which extends object and implements runnable. We override the runnable method. We log to our console our different states. Entering run method, in run current thread, we get the current thread. We enter into a loop that's true, and we put our thread asleep until it's interrupted. We also print out that we're woke up again, and finally when we're leaving run. Now let's look at our main method. We instantiate the demo class, call it daemon thread. We output to our console that we're entering main. We also instantiate a thread and we pass in our daemon thread. We call the set daemon to true. The difference here is calling the method set daemon. This method marks this thread as either a daemon thread, true, or a user thread, false. The Java Virtual Machine exits when only threads running are all daemon threads. This method must be called before the thread is started. Then we start our thread. We put our thread asleep for some time and we wait for an interruption exception. and we print to the console that we're leaving main. Let's run our program and see this behavior on the console. And let's look at the order of execution. Right-click on the source, run as Java application. We can see here that it entered main first, then it entered run. We were in the run method for some time, and finally we exited completely the main method. This concludes our discussion of daemon threads in Java. In this video, we will introduce thread states within the Java programming language. While a thread is alive, it is in one of several states. On a single processor system, only one thread is actually running at a time. The other threads are either blocked or are ready to run and waiting for a turn on the processor. The thread scheduler controls which one of the ready-to-run threads is actually running on the processor. Only one thread is actually in the running state at any given time. All the other threads that are ready to run wait to be picked up by the thread scheduler. Thread priority helps the thread scheduler choose which of the ready-to-run threads should be run next. Threads can be blocked in one of four states. When a thread executes thread.sleep, it blocks until the specified number of milliseconds passes or until it is interrupted by another thread. When a thread encounters a wait statement block, it is blocked until it is notified, interrupted, or the specified number of milliseconds elapses, if a timeout was specified. By looking at code, we can see how the different changes of state occur in a thread. Here we have two variables that communicate our state, waiting and ready. Our demo class extends thread and overwrites run. Here we are basically checking to see if our thread is waiting. We call the method startWait that goes into a loop and calls wait on the thread. And it waits until it's interrupted. We also put it to sleep and we wait till it's interrupted there. When notice is called on the thread, it changes the instance variable ready to true and it notifies all the other threads. Let's uncomment this code out. And we can see that we create here an instance of the demo, call it demo thread. And we're going to create a method called print thread status. So let's implement that. And we're going to use the methods to be able to get the state of the thread and also to see if it's still alive. Okay, here we have our method signature. And we're going to print to the console what our thread state is. First, we'll get the name. Then we'll get the alive status. And then we'll get the state. If we look at here, thread is alive. It tests if this thread is alive. A thread is alive if it has been started and has not yet died. Now let's look at this getState method. This returns the state of this thread. This method is designed for use in monitoring of the system state, not for synchronization control. Now we're going to run our program and we can see the different changes in state. Right click on source, run as Java application. We can see that the demo thread checked to see if it was alive and its state was new. And after that it started. It was waiting and alive, and then we find it terminating and a state changing to terminated. This concludes our discussion of thread states in Java. In this video, we will introduce synchronization within the Java programming language. There are many situations in which multiple threads must share access to common objects. Previous examples have used multi-threading by having multiple executing threads write to the Java console, a common shared object. These examples have not required any coordination or synchronization in the way the threads access the console window. Whatever thread is currently executing was able to write to the console window. No coordination between concurrent threads was required. There are times when you might want to coordinate access to shared resources. For example, in a database system, you might not want one thread to be updating a database record while another thread is trying to read it. Java enables you to coordinate the actions of multiple threads using synchronized methods and synchronized statements. An object for which access is to be coordinated is accessed through the use of synchronized methods. These methods are declared with the synchronized keyword. Only one synchronized method can be invoked for an object at a given point in time. This keeps synchronized methods in multiple threads from conflicting with each other. Let's walk through an example. Here we have an array holding our values to print to the console. Our threads run method will call our synchronized list. In our main method, we create two threads and start them both. Basically, we continue to loop while both threads are always alive. Our method displayList has the keyword synchronize, which enables a simple strategy for preventing thread interference and memory consistency errors. If an object is visible to more than one thread, all reads or writes to that object's variables are done through synchronized methods. The displayList method uses the current thread method of class thread to reference the current thread in order to invoke random wait. Now we have to run our program and watch its output. Right-click on the source, run as Java application. It says VTC and Java are hot, rock, and inspiring. Each thread prints out our array of messages. Now let's remove the synchronized keyword in the declaration of the displayList method And let's see if there's a difference in the program's output and observe the effects of synchronization upon multi-threaded program execution. So we remove the synchronized keyword, right-click on the source, run as Java application. Now we can see here that when display list is not synchronized, it may be invoked by one thread, say thread 1, display some output, and wait while thread 2 executes. When thread 2 executes, it too invokes display list to display some output. Two separate invocations of display list, one for thread 1 and the other for thread 2, execute concurrently. This explains the mixed output displayed. When the synchronized keyword is used, thread 1 invokes display list, acquires a monitor for the synchronized output class, because display list is a static method, and display list proceeds with the output display for thread 1. Because thread 1 acquired a monitor for the synchronized output class, thread 2 must wait until the monitor is released before it is able to invoke display list to display its output. This explains why one task output is completed before the others. This concludes our discussion of synchronized in Java.